There is a sound in the universe so powerful it can shake the very fabric of reality, yet it makes no noise at all. It is a silent scream, a ghost of a cataclysm that travels for over 1 billion years to reach us carrying a story of unimaginable violence and creation. This is not a sound that travels through the air, for in the void there is no air to carry it. This is a sound that travels in space-time itself, a vibration in the geometry of the cosmos. To hear it, you do not need ears, you need an entirely new sense, a way to feel the very arena of existence tremble. For millennia we were deaf to this cosmic symphony, blind to the universe's most titanic collisions. We lived on the shore of a vast silent ocean, unaware of the leviathans battling in its depths. But that has all changed. We have finally learned to listen, and the first thing we heard was the sound of monsters colliding. Imagine if you can two ghosts in the machine of the cosmos. They are not made of matter in any way we would recognize. They are the triumphant endpoints of gravity, the final victory of mass over every other force in nature. Each one is a black hole, a point of infinite density cloaked in a sphere of perfect darkness, an event horizon from which not even light, the fastest thing in creation, can escape. For hundreds of millions of years they have been partners in a deadly gravitational waltz. One was perhaps 36 times the mass of our Sun, its companion a slightly more modest 29. Born from the collapse of colossal brilliant blue stars in a galaxy far, far away, they found each other in the void, their immense gravities locking them into an orbit of slow, inexorable decay. They were a binary system, a pairing of cosmic predators destined for a singular violent fate. For eons their dance was elegant, almost stately. They circled one another across millions of miles, two voids sweeping through the cosmos. But with every pass, every single gravitational embrace, they radiated away a tiny amount of their orbital energy. Not as light, not as heat, but as infinitesimal whispers in the structure of space-time. These whispers are gravitational waves, and they are the engine of this system's doom. With each wave that propagated outwards, the black holes drew a fraction of an inch closer. Their orbit tightened. Their speed increased. What began as a majestic slow waltz across cosmic timescales began to accelerate the tempo, quickening over the final few million years. The space between them shrank from the distance between stars to the distance between planets, and still they fell toward one another. In the final few minutes, the scene transforms from a cosmic ballet into a chaotic gravitational vortex of almost unimaginable power. The two black holes are now whipping around their common center of gravity at a significant fraction of the speed of light. They are so close that the very concept of empty space between them begins to lose its meaning. The geometry of the universe in their immediate vicinity is no longer the gentle, predictable curvature we experience around our Sun. It has become a churning, twisting, distorted storm. Spacetime is being dragged around with them like water caught in a blender, a phenomenon known as frame dragging magnified here to a terrifying extreme. Light from distant stars that passes too close would be bent into pretzel-like shapes, its path so contorted that the sky around the merging giants would look like a funhouse mirror reflecting a warped and broken cosmos. They are now mere hundreds of miles apart, two perfect spheres of absolute black swallowing any stray photons and casting no shadows, their presence betrayed only by the profound gravitational chaos they inflict upon their surroundings. The tidal forces are stupendous. If you could place a moon between them, it would be instantly shredded into a stream of superheated plasma. A star would be unraveled like a ball of yarn, its material siphoned off and torn apart atom by atom. But here there is nothing left to destroy but each other, and the very stage on which their final act is set. The two event horizons, those one-way membranes that define the boundaries of each black hole, begin to distort. They stretch and deform, pulled into teardrop shapes, reaching for one another across a final, rapidly closing abyss. The point of no return is no longer a simple sphere. It has become a dynamic, quivering surface, a testament to the gravitational violence being unleashed. And then, in the last fraction of a second, it happens. The two horizons touch. For an infinitesimal moment, a bridge forms between them, a fleeting shape of impossible geometry, connecting two separate regions of infinite gravity. It is a moment of profound cosmic transition. They are no longer two, but one. The two singularities, the theoretical points of infinite density at their cores, spiral towards their unified destiny inside this newly formed larger event horizon. This new black hole is a monster born from the fusion of two titans. It is not the simple sum of their parts. In that final violent instant of coalescence about 3 times, the entire mass of our Sun, 3 solar masses of pure existence, is not absorbed into the new entity. Instead, it is converted with perfect efficiency, according to Einstein's most famous equation, E=mc2, directly into raw, untamed gravitational energy. It is a conversion of matter into spacetime curvature on a scale that dwarfs any other process in the known universe. Think of it, in less than 1/10 of a second, this single event releases more energy than all of the stars in all of the galaxies in the entire observable universe combined. It is a blast of pure gravity, an explosion not of space, but in space. It is a celestial blowtorch that radiates no light. It is a cosmic thunderclap that makes no sound. This colossal release of energy erupts outwards from the merger not as fire or radiation, but as a tidal wave of gravitational radiation, a tsunami of spacetime. This is the death scream of the binary system, a final ringing pronouncement of its union that travels across the cosmos at the speed of light. This gravitational wave is a physical ripple in the metric of space. As it passes through you, it would stretch you vertically while squeezing you horizontally, then stretch you horizontally while squeezing you vertically, oscillating back and forth. The effect is impossibly small, a distortion far tinier than the nucleus of a single atom, yet it is the unmistakable signature of the event, its enduring obituary etched into the cosmos itself. This incredible phenomenon, this quivering of the cosmic drum, was not discovered by accident. It was predicted. It was imagined over a century ago in a world lit by gas lamps and powered by steam, a world that had not yet split the atom or left its own atmosphere. It was conceived in the mind of a single man, Albert Einstein. In 1915 he unveiled his general theory of relativity, a revolutionary new vision of the universe that overturned 250 years of Newtonian physics. In Einstein's universe, gravity was not some mysterious invisible force that reached out across space to pull objects together. Gravity, he proposed, was the consequence of mass and energy warping the very geometry of the universe. He asked us to imagine space-time as a flexible 4-dimensional fabric. A planet, a star, or a galaxy is like a heavy ball placed on this fabric, creating a dimple, a depression. The orbits of other objects are not the result of being pulled by a force, but are simply the result of them following the straightest possible path through this newly curved, distorted geometry. It was a beautiful, elegant, and profoundly strange idea. But within this new mathematical framework, Einstein found something even stranger, a hidden consequence of his own equations. If this space-time fabric could be bent, he reasoned then, it must also be able to ripple. If a massive object were to accelerate or move violently, it should create waves in the fabric, much like a thrashing hand creates waves in a pond. These gravitational waves, he calculated, would propagate outwards, carrying energy and information about whatever cataclysmic event had created them. He had on paper discovered the sound of the universe. Yet even for a mind as audacious as Einstein's, the practical implications seemed beyond reach. He did the calculations himself and realized that these waves, by the time they reached Earth from any conceivable astronomical source, would be infinitesimally weak. The stretching and squeezing of space-time they would produce would be so small, so subtle, that he believed no instrument could ever be built to detect them. For him they were a fascinating but ultimately unobservable quirk of his theory, a ghost in his beautiful machine. For the better part of a century, that is exactly what they remained. Gravitational waves were the stuff of theoretical physics, a mathematical curiosity confined to chalkboards and academic papers. While astronomers opened new windows onto the cosmos with radio telescopes, infrared observatories, and X-ray satellites, the gravitational universe remained entirely dark, entirely silent. The search for these elusive ripples was considered a fringe science, a quixotic quest for something that might not even be real, and was certainly, as the great man himself had suspected, impossible to find. But the dream refused to die. A handful of visionary physicists armed with extraordinary patience and an unshakable faith in Einstein's theory began to wonder what if he was wrong. Not about the waves themselves, but about our ability to one day hear them. What if we could build a machine sensitive enough not just to prove they exist, but to use them to see the universe in a completely new light? The challenge was monumental, bordering on the insane. It required building the most sensitive measurement device in human history. The plan that eventually emerged was an experiment of breathtaking scale and ambition, the Laser Interferometer, Gravitational Wave Observatory, or LIGO. It is a machine built to measure a change in distance 1,000 times smaller than the width of a single proton. To achieve this, scientists constructed two identical L-shaped detectors, one in Livingston, Louisiana, and the other in Hanford, Washington, separated by nearly 2,000 miles. Each arm of the L is a perfectly straight 2.5-mile-long vacuum tube, the straightest and emptiest sustained vacuums on the planet. Down these tubes, a powerful laser is split into two beams. These beams travel down the arms, reflect off perfectly polished mirrors, and return to the starting point to be recombined. The entire apparatus is a gravitational tympanum, a cosmic microphone of planetary proportions. In the quiet, undisturbed state, when the two laser beams recombine, they are perfectly out of phase and cancel each other out, creating darkness at the detector. But if a gravitational wave born from some distant cosmic catastrophe were to wash over the Earth, it would minutely stretch one arm of the detector while simultaneously squeezing the other. This tiny, fleeting distortion in the length of the arms would knock the two laser beams out of perfect cancellation. For a brief moment, they would no longer completely nullify each other. A flicker of light would appear at the detector, a signal of the disturbance. For years, these incredible machines listened, sifting through the constant seismic noise of our own planet, the rumble of distant trucks, the crashing of ocean waves, the subtle shifting of tectonic plates, all in search of a single authentic whisper from the depths of space. They were listening for the sound of Einstein's ghost. Then, on September 14, 2015, just as the newly upgraded detectors were being calibrated for their first official run, the universe decided to speak. A signal arrived, a ghost from 1.3 billion years in the past. It appeared almost simultaneously at both the Louisiana and Washington sites, a clear, unambiguous tremor that stood out starkly from the background noise. It was not a random blip. It was a waveform, a shape that matched with breathtaking precision the exact signal that theorists had predicted for the merger of two black holes. The signal began as a low-frequency hum, the signature of the two objects in their final wide orbits. Then, over the course of just 0.2 of a second, the wave rose in both frequency and amplitude, creating a characteristic ascending sound. It was a chirp, a cosmic crescendo. This was the sound of the two black holes whipping around each other hundreds of times a second, closer and closer, faster and faster, screaming their existence into the fabric of space-time. The chirp climaxed with the final violent collision and was followed by a brief fading ringdown, the vibration of the newly formed single black hole settling into its final stable form. In the control rooms there was stunned disbelief, followed by a wave of quiet, exhilarating certainty. A century of theoretical prediction, decades of tireless and often thankless engineering, and billions of dollars of investment had all culminated in this single ephemeral chirp. It was the confirmation of one of Einstein's most profound and elusive ideas. It was the first direct detection of a binary black hole system. It was the first time humanity had ever observed two black holes merging. It was in every sense of the word the dawn of a new era. We had been like astronomers who had spent their entire history without a telescope, and someone had just handed us the Hubble. We had been deaf to the universe's most dramatic events, and now, for the first time, we could hear. The silence was broken. The cosmic ocean was no longer mute. That single, fleeting signal has changed everything. It has opened an entirely new, non-electromagnetic window through which to view the cosmos. It gives us a new sense, a way to perceive the universe not through light, but through the rhythm and pulse of gravity itself. This raises a cascade of profound questions, questions that will define astronomy for the next century. What hidden secrets of the cosmos can these monstrous collisions, these silent screams now reveal to us? What can they tell us about the lives and deaths of the most massive stars, the enigmatic factories that forge black holes in the first place? How are these violent mergers connected to the creation of the heaviest elements in the universe, the gold in our jewellery, the platinum in our electronics? Can the precise shape of their gravitational song allow us to test the limits of Einstein's theory of gravity in the most extreme environments imaginable, where his equations might finally break down? With this newfound ability to listen in on the universe's most secret and violent conversations, we are poised, on the edge of discovery, tuning our instruments to a symphony of creation and destruction that has been playing unheard since the dawn of time. We are just beginning to learn its language, and we are finally ready to hear its stories. Is it possible that the deepest silence in the universe is not one of peace, but of profound, unimaginable violence? For a century we believed the cosmos was a silent movie, a grand pantomime of wheeling galaxies and exploding stars all playing out without a sound. We were deaf to its true nature, deaf to the most powerful events since the dawn of time. We were listening for the wrong thing. The story of how we learned to hear the universe's scream begins not in the heavens, but on a piece of paper in the mind of a single man who dared to reimagine reality. In 1915, Albert Einstein gave us his theory of general relativity, and in doing so he tore down the 300-year-old house of Newtonian physics and built a cathedral in its place. For Newton, gravity was a mysterious instantaneous force, an invisible rope pulling objects toward one another. For Einstein, there was no rope, there was no force, there was only the geometry of existence itself. He revealed that space and time are not a static empty stage upon which the cosmic drama unfolds. Instead, they are a single unified entity, space-time, a dynamic flexible fabric woven from the very essence of the universe. Mass and energy, he proposed, tell this fabric how to curve. A planet, a star, a galaxy. They don't pull on things. They create a dip, a warp, a profound depression in space-time, and in turn that curvature tells matter how to move. Planets orbit the sun not because they are tethered to it, but because they are following the straightest possible path through the curved space created by the sun's immense mass. They are cosmic marbles rolling around a gravitational well. It was a vision of exquisite, breathtaking elegance. His equations, a mere handful of symbols, describe the graceful dance of planets and the majestic sweep of galaxies with unparalleled precision. But buried deep within that elegant mathematics, hiding in the darkest corners of his beautiful new reality, was a monster. A mathematical prophecy of such absurdity, such violence, that even Einstein himself could not bring himself to believe it. The equations permitted a solution where, if you could concentrate enough mass into a small enough volume, the curvature of space-time would become infinite. The fabric wouldn't just dip, it would puncture. It would tear through to a point of zero volume and infinite density. A singularity. This wasn't just a prediction, it was a breakdown. A place where the laws of physics, his own included, would cease to have any meaning. A point where gravity becomes so overwhelmingly powerful that it crushes everything, even the structure of reality itself, out of existence. For this to happen in the real universe, you would need an engine of unimaginable power, a cosmic press capable of squeezing a star to an infinitesimal point. And that is precisely what nature had waiting in the wings. For billions of years, a massive star lives a life of cosmic balance. Deep within its core, a thermonuclear furnace rages, fusing lighter elements into heavier ones. This process unleashes a torrent of energy, a constant outward pressure that pushes against the star's own colossal gravity. It is a stalemate between creation and annihilation, lasting for millions of glorious light-filled years. But this celestial balancing act cannot last forever. Eventually the star exhausts its nuclear fuel. The furnace sputters and dies. With its primary weapon against gravity now silenced, the stalemate is broken in an instant. Gravity, the patient, relentless force, finally wins, and it wins catastrophically. In less than a second, the star's immense outer layers collapse inward at nearly a quarter of the speed of light. They slam into the now impenetrable core and rebound in the most spectacular explosion the universe can muster, a supernova. For a few brilliant weeks, this single dying star can outshine its entire home galaxy, a final defiant roar of light. But what of the core left behind? If the original star was massive enough, more than 20 times the mass of our Sun, then no known force in the universe can halt its continued collapse. Not the pressure of atoms, not the quantum mechanics of electrons, nothing can stop gravity's final absolute victory. The core continues to crush itself smaller and smaller, the density skyrocketing to unimaginable levels. The curvature of space-time around it deepens, steepens, becoming a vortex from which nothing can escape. At a critical threshold, a point of no return is forged, an invisible border in space called the event horizon. It is not a physical surface you could touch, but a boundary in the very geometry of reality. Cross it, and all paths, all possible futures lead only one way inward toward the singularity at the centre. Not even light, the fastest thing in the universe, can escape. Space itself is flowing inward faster than light can flee. A black hole is born, a region of space-time cut off from the rest of the universe, a gravitational tomb sealed for eternity. For decades, these objects remained phantoms of mathematics. Fascinating, terrifying, but surely not real. Many leading astronomers considered them a mathematical quirk, an artifact of applying a perfect theory to an imperfect universe. How could you even find something that by its very definition emits no light, no heat, no information? How do you hunt a ghost? The answer, it turned out, was to look not for the ghost itself, but for the chaos it leaves in its wake. In the 1960s, astronomers turned their new X-ray telescopes toward the constellation Cygnus the Swan. There they found a powerful flickering source of X-rays named Cygnus X1. It was a colossal blue supergiant star, a magnificent vibrant object. But something was wrong. Analysis of its light showed the star was wobbling, orbiting an unseen companion every 5.6 days. Calculations revealed this invisible partner was a heavyweight weighing in at over 15 times the mass of our Sun. Yet it was completely dark. A star that massive should have been one of the brightest objects in the sky. Unless, of course, it was no longer a star. Here was the first piece of compelling tangible evidence. We could not see the black hole, but we could see its gravitational tyranny. We could see it feasting. The black hole's immense gravity was siphoning gas from the outer layers of its companion star. This stolen material didn't fall straight in. Instead, it formed a swirling superheated structure called an accretion disk, a cosmic drain spiraling into oblivion. As the gas particles jostled and accelerated to near-light speed, friction heated them to millions of degrees, causing them to scream in the high-energy language of X-rays. This was the source of the flickering glow from Cygnus. It was the death cry of matter, the last broadcast from the edge of forever. The case was building. Black holes were not just theory. They were real lurking predators in the cosmic darkness. But this discovery opened the door to an even more profound question. The universe, it seems, rarely creates in isolation. Look across the cosmos, and you see that companionship is the rule, not the exception. Stars are social creatures. More than half of the most massive stars, the kind destined to become black holes, are born not alone but in binary pairs, gravitationally bound from birth. They spend their entire lives locked in a celestial waltz, orbiting a common centre of gravity for millions of years. Two titans pirouetting through the void. So you're forced to ask the ultimate question, what happens when the dance is over? What happens when both of these stellar partners, one after the other, exhaust their fuel and collapse under their own weight? What happens when you are left with not one black hole, but two orbiting each other in the silent darkness? You are left with a binary black hole system. Two perfect gravitational abysses, two punctures in reality, locked in a final intimate embrace. And with this theoretical possibility, we returned once again to the prophetic pages of Einstein's equations. Because his theory didn't just describe a static curved space-time, it also predicted something far more dynamic, far more subtle. Einstein realized that if the fabric of space-time can be bent by mass, it could also be disturbed. An accelerating mass, he calculated, should create ripples in the geometry of space-time spreading outward at the speed of light. These are not waves travelling through space like sound or light. They are waves of space itself, gravitational waves. As a wave passes by, it literally stretches and squeezes the fabric of reality. Distances between objects will momentarily expand along one direction and contract along a perpendicular direction. The effect is infinitesimal, almost imperceptible. For most of a century, it was another of his predictions that seemed destined to remain an untestable curiosity. What could possibly be powerful enough in the universe to generate ripples that we could ever hope to detect? The answer was waiting for us in that dark theoretical dance. A binary black hole system is the ultimate gravitational wave generator. As these two colossal objects orbit each other, these two warps in space-time circling one another, they're constantly churning the fabric of the universe. This process radiates energy away from the system not as light, but in the form of these gravitational waves. They are bleeding their orbital energy into the cosmos, and as they lose energy, their orbit must shrink. They get closer. For eons, this process is achingly slow. Over hundreds of millions or even billions of years, the two black holes spiral gently inward. Their gravitational waltz grows ever so slightly tighter. The distance between them, once measured in millions of kilometers, shrinks to thousands, then hundreds. But as they get closer, the rate of energy loss skyrockets. The inward spiral accelerates, transforming from a graceful dance into a frantic, inescapable death spiral. In the final minutes of their existence as a pair, they are whipping around each other hundreds of times a second, moving at a significant fraction of the speed of light. The serene geometry of space-time around them is twisted into a violent churning vortex. The gravitational waves they are now emitting become a storm, a tsunami of space-time distortion carrying away unfathomable amounts of energy. This storm has a sound, a characteristic signature, that was predicted with stunning accuracy by theorists decades ago. As the black holes get faster and closer, the frequency of the gravitational waves they emit increases. If we could translate these vibrations into sound, we would hear a tone slowly rising in pitch. A low-frequency hum building over billions of years, accelerating into a final piercing crescendo. The chirp. Then in the last fraction of a second, the inevitable happens. The two event horizons, the two borders of nothingness touch. They merge. In that instant, a single new larger black hole is born, but it is not born peacefully. The new object is a distorted, quivering blob of space-time violently vibrating as it settles down into its final spherical shape. This ringdown phase unleashes one last spectacular burst of gravitational waves, a final shout into the cosmos, before it settles into an eternal perfect silence. The numbers involved in this final moment are simply beyond human comprehension. In that fraction of a second of the merger, an amount of mass several times the mass of our Sun is instantly converted into pure gravitational energy, according to ESMC2. The power radiated during this single event is more than 50 times greater than the combined power output of every star in every galaxy in the entire observable universe. Imagine all the light of the cosmos focused into a single moment. The merger of two black holes is vastly more powerful than that. It is the most energetic event we know of since the Big Bang itself. A silent, invisible explosion of pure gravity. For a century, this was the end of the story. A magnificent theoretical prediction, a symphony of destruction played out on the blackboard of physicists, but one we were destined never to witness. Because by the time these ripples of space-time travel across millions or billions of light-years to reach us here on Earth, their power is dissipated almost completely. The effect is staggeringly small. The predicted stretching and squeezing of space is minuscule, a change in distance of less than 1/10,000th the diameter of a single proton measured over a distance of several kilometers. It is an impossibly small signal buried in the noise of our geologically active trembling planet. Detecting it seemed like a fantasy. It would be like trying to measure the thickness of a single sheet of paper, while that paper is sitting on the deck of an aircraft carrier during a hurricane from a satellite in orbit. The theory was complete, the prediction was clear. A new window on the universe was waiting to be opened, but it was locked behind an engineering challenge so audacious, so monumentally difficult, it would require a generation of scientists to build the key. They would have to build a machine sensitive enough to feel the vibrations of space-time itself. They would have to learn how to hear the silence, To even conceive of such a machine was to declare war on the very fabric of our world. A war not of force, but of stillness. Not of destruction, but of impossible quiet. The theoretical elegance of Einstein's waves, those gentle cosmic breaths, collided with the brutal, messy reality of a noisy planet. The challenge was almost mythological in its scale. You're not trying to see something, or even to hear something in the conventional sense. You're trying to feel the universe itself stretch and compress. You're trying to measure a change in distance 1,000 times smaller than the nucleus of a single atom. It is a distortion so infinitesimal that the rumble of a truck on a distant highway becomes a deafening cataclysm. The whisper of wind through a desert bush becomes a seismic roar. The rhythmic crash of ocean waves on a coastline hundreds of miles away is a planetary drumbeat drowning out the subtle symphony of the cosmos. How then do you build an instrument that can ignore the entire Earth, yet listen for the echo of a collision that happened 1 billion years ago? You don't build a machine. You must construct an island of perfect silence, a sanctuary from physics itself, and float it in the middle of our chaotic world. The idea chosen for this monumental task was at its heart an echo of the 19th century, a concept of brilliant simplicity scaled up to an ambition that bordered on madness. It was called an interferometer. Imagine splitting a single pure beam of light in two. You send these two twin beams on journeys of their own down two identical paths perfectly perpendicular to one another. At the end of each path you place a flawless mirror. The beams strike the mirrors and race back to the exact point where they were split. If the two paths, the two arms of this colossal L, are precisely the same length, the returning light waves will meet and merge in perfect harmony. They will cancel each other out in a process called destructive interference, and your detector will see only darkness. It's a trick of light, a delicate balancing act on a knife edge of physics. But what if something were to disturb this perfect symmetry? What if a gravitational wave born from the death spiral of two black holes washed over the Earth, as this ripple of space-time passes through it, would stretch one arm of your instrument by an unthinkably small amount while simultaneously squeezing the other? Suddenly the two paths are no longer identical. One beam of light arrives back a fraction of a femtosecond late. The two waves, once perfectly out of sync, are now slightly misaligned. They no longer cancel each other out completely. And in that darkness a flicker of light is born. That flicker, that ghost of a signal, is the prize. It is the sound of space-time ringing. This was the principle behind the Laser Interferometer Gravitational Wave Observatory, or LIGO. But to turn this elegant concept into a functioning reality required building on a scale that defied intuition. The arms of the interferometer couldn't be a few meters long on a laboratory bench. To give a gravitational wave subtle stretching and squeezing enough distance to register, the arms had to be enormous. They settled on a length of 4 kilometers, 2.5 miles of a laser light travelling in a near-perfect vacuum. Humanity's cosmic ears would be two identical L-shaped leviathans planted on the surface of the planet itself. They needed to be far apart to ensure that any signal detected wasn't just some local tremor or fluke. One was constructed amidst the humid pine forests of Livingston, Louisiana, a place of damp earth and thick air where the ground itself is soft and yielding. The other was raised from the arid, windswept scrubland of the Hanford site in Washington state, a place of dry soil and profound emptiness. Two listening posts separated by 3,000 kilometers, forming a planetary-scale detector waiting. Their sole purpose to simultaneously feel the same infinitesimal shudder from the depths of space. To build them was an engineering odyssey that would span decades and consume the careers of thousands of scientists and engineers. It began with the tunnels, 2.5 miles of concrete and steel stretching to the horizon. Within them lay the vacuum chamber's stainless steel tubes, over 1 meter in diameter, polished to a mirror sheen. Inside these tubes, engineers had to create one of the largest and most pristine vacuums ever achieved on Earth. They had to pump out over 10,000 cubic meters of air, expelling quintillions of molecules, until the pressure inside dropped to 1/trillionth of the atmosphere around us. A single stray air molecule drifting into the laser's path would be enough to scatter the light and create a false signal, a phantom noise that would utterly blind the instrument. It took 40 days of continuous pumping just to reach the required emptiness, creating a void purer than almost anywhere in the solar system, a sealed highway for light. And at the end of this highway, the mirrors. These were not mere pieces of silvered glass. They were perhaps the most perfect physical objects ever crafted by human hands. Forged from ultra-pure fused silica, they were polished so exquisitely that their surfaces deviated from a perfect curve by less than the diameter of a single atom. If you were to scale one of these mirrors to the size of a continent, the largest imperfection, the highest mountain, would be no bigger than a grain of sand. They were designed to be near-perfect reflectors, but also to be utterly profoundly still. Yet this is where the true war against noise began, for no object is ever truly still. The mirrors suspended at the heart of the machine were hostages to the ceaseless vibration of the earth. A passing train, a distant earthquake, even the gentle footsteps of a scientist walking in the control room, each was a source of seismic noise that could shake the mirrors by 1,000 times more than the signal they were searching for. To shield them, the LIGO team engineered a system of isolation that was nothing short of miraculous. Each 40-kilogram mirror, a gleaming puck of frozen light, was suspended by delicate steel wires within a multi-stage pendulum. This pendulum itself hung from another, which in turn was mounted on a platform equipped with sensors and actuators, an active damping system that could feel the slightest vibration and push back against it in real time. It was like trying to balance a needle on its tip on the deck of a ship in the middle of a hurricane. This entire construct, a gravitational gyroscope of nested pendulums and active feedback loops, was designed to create an oasis of tranquility, a pocket of space-time so isolated from the planet that it could feel the faint touch of the cosmos. But even if you could silence the shaking of the Earth, you faced a deeper, more insidious enemy heat. The universe is never at absolute zero. Every atom in the mirrors, in the suspension wires, in the very structure of the observatory possesses thermal energy, and this energy causes them to jiggle, to vibrate in a random microscopic dance. This is thermal noise, the ceaseless shimmering hum of a world that is not frozen solid. For LIGO, this atomic shivering was a nightmare. A mirror's surface, though polished to perfection, was a roiling sea of vibrating atoms. The suspension fibers meant to be silent tethers were vibrating like violin strings played by a microscopic ghost. Each of these random jitters could mimic the signature of a gravitational wave, creating a storm of false positives. The team had to invent new mathematical models, new ways of understanding and subtracting this thermal chatter from the data. They had to use materials with incredibly low mechanical loss materials that could ring like a bell for hours without losing energy, ensuring that any thermal motion was confined to very specific frequencies that could be filtered out. The challenge drove materials science into uncharted territory, pushing the limits of what we could create and measure. And yet beyond the rumbling earth and the shimmering heat there lay a final, almost philosophical barrier, a ghost woven into the very mathematics of reality. Quantum mechanics itself became the adversary. Light, the very tool being used to measure space-time, is not a continuous stream. It is made of discrete packets of energy photons. To get a more precise measurement of a mirror's position, you need to hit it with more photons. But each photon, upon striking the mirror, imparts a tiny push, a kick of momentum. This is called radiation pressure, so the more accurately you try to measure the mirror's position, the more you disturb its momentum, making its future position less certain. This is the Heisenberg uncertainty principle writ large in a 4-kilometer machine. Conversely, if you use fewer photons to reduce the kick, you get a fuzzier, less certain picture of the mirror's position, a phenomenon called photon shot noise. The scientists were trapped in a quantum paradox. Squeeze the uncertainty in one place, and it pops up somewhere else. They were walking a tightrope, trying to find a delicate balance in the quantum foam, designing a system that could momentarily cheat uncertainty itself. With these monumental challenges addressed, the great machines were finally switched on in the early 2000s. The laser, a beam of infrared light more stable than any ever built, was fired into the void. The mirrors floating in their sanctuaries of silence began their vigil. The control rooms, filled with screens displaying endless streams of data, fell into a quiet hum of anticipation. And then, nothing. Days turned into weeks, weeks into months. Months bled into years. The data streams flowed, but they carried only the noise of our own world. the teams refined their analyses. They developed sophisticated computer algorithms to search for the faintest hint of a signal buried in the static, a specific chirp that would signal the final violent merger of two massive objects. They hunted and they listened. But the cosmos remained stubbornly profoundly silent. Within the scientific community, patience began to wear thin. The initial thrill and optimism gave way to a long grinding period of doubt. LIGO became to some a cautionary tale, a magnificent, fantastically expensive instrument, built to chase a phenomenon that might be too rare or too weak to ever be found. Was it a noble failure, a testament to an ambition that had simply outstripped the available technology? The scientists running the experiment faced a quiet, mounting pressure. Their colleagues in other fields of physics were discovering new particles at the Large Hadron Collider, mapping the distant universe with new telescopes. And the LIGO team had only silence to show for their decades of work. They found instrumental glitches. They found noise that mimicked a signal, sending hearts racing in the control room for a few hours, before being identified as a mundane artifact. There were even blind injections, secret fake signals inserted into the data by a small part of the team to test if the analysis groups could find them. They could. The system worked. The machine was capable, but the universe, it seemed, was not talking. Yet the belief never truly died. The teams knew that this first iteration of LIGO was always understood to be a pathfinder, a pioneering effort that was pushing at the very edge of what was possible. It might not have been sensitive enough. The universe of gravitational waves might be quieter than the most optimistic predictions. So they made a decision of breathtaking boldness. They would not just tweak the machine, they would rebuild it from the ground up. This was the birth of advanced LIGO. It was a complete technological rebirth. The original steel vacuum tubes remained the concrete shell of the beast, but its heart and soul would be entirely new. The mirrors were heavier 40 kilograms of pure silica, allowing them to be less susceptible to quantum pressure. The suspension system was completely redesigned, an even more complex series of pendulums and active dampers to further quell the seismic noise. The laser was vastly more powerful and more stable, a pure tone of light that would allow for even greater precision. The entire endeavour was a gamble on an almost unfathomable scale. The upgrades were designed to make advanced LIGO 10 times more sensitive than its predecessor. And because sensitivity to gravitational waves increases with the cube of the distance, you can probe this tenfold improvement didn't just mean they could hear 10 times better. It meant they could search a volume of space 1,000 times larger. They were not just opening a window a little wider. They were tearing down the wall and hoping to be met not with silence, but with a roaring, vibrant, previously invisible cosmos. By 2015, after years of painstaking installation and calibration, the new machines were almost ready. The twin detectors in Washington and Louisiana were being brought online, their systems tested and refined in a final, quiet commissioning run. The years of silence had created a palpable tension. The careers of a generation of scientists had been poured into these cathedral-like instruments. The promise of a new astronomy, a new way of seeing the universe hung precariously in the balance. Was Einstein's last great prediction about to be confirmed in the most spectacular way imaginable, or would the silence simply continue deeper and more profound than ever before? The universe had kept its secrets for a long time. Now, with humanity's most sensitive ears pressed against the fabric of space-time, all anyone could do was hold their breath and listen. After a century of theoretical whispers and decades of meticulous, frustrating, monumental construction, the universe had finally decided to speak. But its first word was not a subtle murmur from the void. It was a cataclysmic shout, a cry so violent it shook the very foundations of reality. The long silence, the agonizing wait you've journeyed through with us was about to be shattered. It happened not with a grand ceremony or a global announcement, but in the quiet, sterile hum of a laboratory just before dawn on a Monday. September 14th, 2015. The newly upgraded detectors of the Laser Interferometer Gravitational Wave Observatory Advanced LIGO were not even officially observing yet. They were in their final engineering shakedown, a last dress rehearsal, before the curtain rose on a new era of astronomy. The teams were stretching the machine's muscles, hunting for the last vestiges of terrestrial noise, chasing down phantom vibrations from passing trucks and distant earthquakes. It was a period of calibration, of refinement, of quiet expectation. No one expected the main performance to begin during the prelude. The signal arrived at 5:51 a.m. Eastern Daylight Time. It struck the detector in Livingston, Louisiana first, a nearly imperceptible tremor lasting less than a quarter of a second. Then, travelling at the speed of a light, the same ripple in spacetime passed through the Earth. 7 milliseconds later, it hit the second detector 3,000 kilometers away in Hanford, Washington. There was no siren, no flashing red light. The event was captured as designed by automated computer systems flagging interesting transient events. To the software, it was just another blip to be sorted, another potential artifact in a sea of noise. But this one was different. This one was unnervingly clean, shockingly powerful, and almost too perfect. Marco Drago, a 33-year-old physicist at the Max Planck Institute in Germany, was the first human being to lay eyes on it. He was performing a routine check of the data pipeline when the alert popped up. He saw a shape on his screen, a simple, elegant curve that sent a jolt of adrenaline through his system. It was a gentle rising tone, a chirp, that swelled in frequency and amplitude before abruptly cutting off. It was the exact signature, the precise death spiral of two massive objects that theorists had predicted for decades. It was the sound they had been straining to hear for a generation. His first thought was not of triumph. It was of deep, profound suspicion. It had to be a test. Throughout LIGO's history, the collaboration had practiced a culture of intense scientific skepticism. To keep the teams sharp and to ensure the integrity of any potential discovery, a small, secret group would occasionally insert fake signals into the data stream. These blind injections were designed to mimic a real cosmic event, perfectly testing the entire system from detection to analysis. Had someone triggered the ultimate final exam just days before the official science run began? The signal was so loud, so textbook perfect, it felt like a caricature of a discovery. The universe, it seemed, shouldn't be this easy, this obvious. The suspicion spread like a contagion through the handful of scientists who were quietly alerted. An email chain began, cautious and coded. They spoke of the trigger, the event, refusing to give it the dignity of a name lest they jinx it. The first order of business was to check the logs. Was there a blind injection scheduled? The answer that came back was a chilling, electrifying no. The system was clean. This was the moment that fear turned into a fragile, terrifying hope. The painstaking process of verification began a global scientific inquest conducted in absolute secrecy. For months, the 1,000+ members of the LIGO collaboration were bound by a pact of silence. A whisper of a discovery of this magnitude could trigger a media frenzy, destroy careers, if it proved to be a mistake, and forever taint the project's credibility. They had to be more than certain. They had to be infallible. The first clue was the time delay. The 7-millisecond gap between the signal's arrival at Livingston and Hanford was precisely what you would expect for a wave travelling at the speed of light, arriving from a particular direction in the southern sky. A local disturbance like a lightning strike or a seismic tremor could not possibly coordinate itself so perfectly across a continent. This was not of the Earth. The data from both detectors were overlaid. They were a near-perfect match, two recordings of the same cosmic scream, one slightly fainter than the other. It was like having two independent, incorruptible witnesses to the same magnificent crime. Now came the Herculean task of peeling the signal away from the noise. Imagine you're trying to hear a single pin drop in the middle of a hurricane. That is the challenge of gravitational wave detection. LIGO is the most sensitive measuring device ever created by humanity, but that very sensitivity makes it vulnerable to a constant barrage of terrestrial interference. The scientists deployed a formidable arsenal of computational tools, algorithms designed to characterize and subtract every conceivable source of noise. They meticulously filtered out the low-frequency rumble of the Earth's crust, the mid-frequency hum of power lines, the high-frequency hiss of thermal vibrations in the mirrors themselves. They cross-referenced every blip with environmental sensors checking for magnetic fluctuations, acoustic anomalies, even changes in the weather. They found nothing. There was no earthly explanation. The signal remained pristine and defiant, a ghost in the machine. A ghost that had travelled for more than 1 billion years to haunt their detectors. The definitive proof came from a process known as matched filtering. For years, supercomputers had been simulating the death throes of binary black holes, generating a vast library of theoretical waveforms, a cosmic catalogue of possible gravitational wave signatures. Each template in this library represented a unique collision, a specific combination of masses, spins, and orientations. The team took the cleaned-up signal from GW 150914 and began to slide it across this library, searching for a match. It was a form of gravitational seance, an attempt to find the spectral fingerprint that corresponded to the observed event. And then they found it. The signal from the detectors locked onto one of the templates with staggering precision. The raw data, that elegant chirp, was an almost flawless mirror of the reality predicted by Einstein's equations. The rising frequency was the two black holes spiraling faster and faster as they drew closer. The soaring amplitude was the sheer violence of spacetime being warped by their gravitational dance, and the abrupt cutoff. That was the moment of fusion, the instant when two distinct horizons dissolved, and a new, single, more massive black hole was born. The silence of the verification process was finally broken by the roar of revelation. This was real. This was it. The decades of doubt, the technical nightmares, the immense personal and financial investment, it had all paid off in less than a quarter of a second. They had not just heard a whisper. They had witnessed a collision of monsters. By analysing the precise shape of the wave, they could resurrect the event, reconstructing the biography of a cataclysm that occurred 1.3 billion years ago, long before multicellular life dominated our own planet. The data told a story of impossible titans. One black hole was approximately 29 times the mass of our Sun. Its partner was even larger, a behemoth weighing in at 36 solar masses. Before this moment, black holes of this size, so-called stellar mass black holes, were largely theoretical. Astronomers had found smaller ones, perhaps up to 15 times the Sun's mass, but nothing on this scale. LIGO hadn't just opened a new window on the universe, it had immediately shown us creatures we never knew existed. And their final dance was a spectacle of unimaginable power. For eons, these two behemoths had circled each other, locked in a gravitational embrace. But in the final moments recorded by LIGO, they were moving at truly insane speeds. As they closed the final gap, they were orbiting each other hundreds of times per second, whipping through space at over half the speed of light. You're watching the most extreme gravitational environment we have ever observed, a place where the fabric of reality is being twisted and torn with a ferocity that defies all earthly comparison. The energy this process unleashed is a number so large it becomes almost meaningless. In that final fraction of a second, the merger of these two black holes converted 3 times the mass of our Sun directly into pure gravitational energy. 3 solar masses vaporized into space-time ripples. The power output of that single event for that brief instant was more than 50 times greater than the combined light of every star in every galaxy in the entire observable universe. It was the most powerful energetic event witnessed by human beings since the Big Bang itself. Think about that. Take all the light, all the heat, all the radiation from trillions upon trillions of stars and multiply it by 50. That is the sheer, unadulterated violence we were eavesdropping on. And yet when this titanic wave finally washed over the Earth, 1.3 billion years later, its effect was infinitesimally small. It stretched and squeezed the 4-kilometre-long arms of the LIGO detectors by less than 1/10,000th the width of a proton. It is a testament to both the feebleness of gravity and the breathtaking ingenuity of the machine built to sense it. But the signal held one last secret. After the crescendo of the merger, there was a final fading oscillation. This was the ringdown. For a fleeting moment, the newly formed black hole, now a single entity of 62 solar masses, was not perfectly spherical. It was a distorted, quivering object wobbling like a struck bell. As it settled into its final stable form, it shed its imperfections as a last gasp of gravitational waves. This ringdown was a direct probe of the event horizon itself, a confirmation that the object left behind was indeed the kind of black hole described by Einstein's general theory of relativity. The announcement came on February 11, 2016. The months of secrecy were over. At a press conference in Washington, D.C., the LIGO leadership finally shared their discovery with the world. The impact was immediate and profound. It was a front-page story on every major news outlet. For scientists, it was the fulfillment of a century-long quest. Einstein's last great prediction, the existence of gravitational waves, was no longer a matter of inference or mathematical beauty. It was a measured physical reality. We could now hear the universe. Astronomy would never be the same. For 400 years we had studied the cosmos through light through the electromagnetic spectrum. We built telescopes to see invisible light, infrared radio waves and X-rays. But light is easily blocked by dust and gas, and many of the universe's most dramatic events, like the collision of two black holes, happen in complete darkness. We were like a deaf person, watching a silent orchestra, seeing the motion of the violin bows but never hearing the music. GWR was SIMFM 914 changed all that. It gave us our hearing. Gravitational waves are an entirely new sense, a fundamentally different way to experience the cosmos. They are not light. They are vibrations in spacetime itself. They travel unimpeded from the most violent and shrouded cosmic engines, carrying pristine information directly from the heart of the cataclysm. This first detection wasn't just a discovery, it was an inauguration. It was the birth of gravitational wave astronomy. The era of silent movies was over. The universe was now a talkie, and it had just delivered its stunning opening line. The single, fleeting chirp from 1 billion years away had validated the life's work of thousands, proven a cornerstone of modern physics, and handed us a key to unlock the dark side of the universe. It demonstrated that pairs of massive black holes not only exist, but that they merge within the lifetime of the cosmos. The event transformed them from a theoretical curiosity into a fundamental player in cosmic evolution. And it posed 1,000 new questions. How do such massive black holes form? How do they find each other and become locked in these fatal binaries? What other unseen monsters were lurking in the dark, waiting to sound their own gravitational alarms? The hunt was on. GW152 was not an end, but a thunderous beginning, a promise of the symphony of cosmic violence that was about to be revealed. That first fleeting chirp from the cosmos was not an ending. It was a beginning. The confirmation of GW1500914 was the sound of a starting gun, and what followed was not a trickle of new information, but a deluge, a thundering cascade of data that would reshape our understanding of the universe's most violent and secretive inhabitants. The pioneers at LIGO and their new collaborators at the Virgo detector in Italy did not rest on their laurels. The discovery was a proof of concept, a shakedown cruise for a new kind of vessel. Now, it was time to truly set sail on the cosmic ocean. Engineers and physicists descended upon the detectors, armed with the knowledge gained from that first precious signal. They hunted down terrestrial noise with a relentless fervour, insulating the mirrors from the faintest tremors of the earth, from the whisper of the wind and the distant rumble of the sea. They amplified the power of the lasers, squeezing even more photons into the 4-kilometre arms, making the rulers of space-time even more precise, more sensitive to the faintest cosmic strains. This was a new phase in our quest. We were no longer listening for a single hoped-for event. We were now conducting a census. We were opening the great book of the universe and turning to a chapter that had until this moment been written in invisible ink. And as the upgraded detectors began their new observation runs, the universe began to speak to us again. Not with a single voice, but with a chorus. Another chirp, then another, and another. The events started to accumulate, each one a ghost story told across 1 billion years, a final scream from a dying couple. GW1000-226 arrived on Boxing Day of 2015, a lighter, more delicate signal. This was not a collision of titans like the first event. These were smaller black holes, one just 14 times the mass of our Sun, the other only 7.5. They circled each other for far longer in the detector's sensitive frequency band, their death waltz more intricate, offering us a clearer view of the final moments. Then came GW1701-4, another merger from a distant corner of space-time, confirming that these events were not a bizarre fluke, but a regular if catastrophic feature of cosmic life. With each new detection, the picture grew richer and far more complex. We were not just finding copies of that first pair. We were uncovering a whole population, a veritable rogues gallery of gravitational monsters, each with its own unique story, its own mass, its own spin, its own dark history. Some were behemoths formed from the merger of black holes that were already shockingly massive, pushing the known limits of what we thought was possible for stellar mass black holes. Others were more modest, yet their very existence in a binary pair posed its own profound puzzles. The initial euphoria of discovery began to give way to a deeper, more challenging phase of inquiry. The what had been answered. We now knew with absolute certainty that binary black holes existed and that they merged, but this triumph only made the next questions burn brighter. The questions of how and why. How do two black holes, the loneliest and most antisocial objects imaginable, end up as gravitational dance partners, locked in an embrace so intimate it will tear spacetime asunder? The journey to discovery had been a climb up a treacherous mountain, and from its peak we saw the breathtaking view of a new landscape. But now we had to descend into that landscape, into the tangled valleys and shadowed forests of astrophysical uncertainty, where every clue seemed to branch into a dozen new mysteries. This was the downward path not of failure but of deepening complexity. The data was pouring in, but the story it was telling was not simple. To understand the problem, you have to appreciate the sheer improbability of it all. Most of the stars in the universe that are massive enough to become black holes are born in pairs, it's true. They blaze into existence together, two brilliant blue giants, tethered by gravity orbiting a common centre of mass. But their lives, and especially their deaths, are fraught with peril that threatens to tear them apart at every stage. This leads us down the first possible path to formation, a story of lifelong companionship known as isolated binary evolution. Imagine two stars born from the same swirling nebula of gas and dust. One is perhaps 40 times the mass of our Sun, its companion 35. They are cosmic royalty, incandescent and powerful, burning through their hydrogen fuel at a furious pace. For millions of years they live as a stable pair, their orbits wide, their lives largely independent. But the more massive star is destined to live faster and die younger. As it exhausts its fuel, it begins to swell its outer layers, bloating into a vast, tenuous red supergiant. Its gaseous envelope expands, reaching out across millions of kilometers of space, and in a moment of sublime cosmic drama, it swallows its own companion whole. This is the common envelope phase, a critical and violent chapter. The smaller star is now no longer orbiting in a vacuum but ploughing through the dense atmosphere of its bloated partner. This creates an immense drag like a handbrake on its orbit. The friction robs the system of orbital energy, causing the two stellar cores to spiral dangerously closer to one another. The process is a frantic race against time. This drag generates enormous heat, eventually becoming so intense that it blows the entire shared envelope of gas away into interstellar space, a glorious expanding nebula. If all goes well, what remains is a stunning sight, the naked, superheated helium core of the giant star, now a Wolf-Rayet star locked in a much, much tighter orbit with its still-living companion. They have survived their first trial. Then the inevitable happens. The massive core runs out of fuel entirely. There is no longer any outward pressure to fight the crushing force of its own gravity. In less than a second, the core collapses. The star dies in the most spectacular way imaginable, a supernova. A blast wave of unimaginable power rips through the system, unleashing more energy in a few moments than our Sun will in its entire lifetime. And here is the second great filter, the second chance for divorce. The explosion itself is rarely perfectly symmetrical. The newborn black hole is often given a natal kick, a powerful shove from the asymmetric blast like the recoil from a colossal shotgun. If that kick is too strong or in the wrong direction, it can easily accelerate the new black hole to escape velocity, flinging it out of the system forever, a lonely wanderer destined for an eternity of solitude. The binary is broken, but if the kick is gentle enough, if the stars were in just the right configuration, the pair can remain bound. Now you have a black hole orbiting a massive living star. The story then repeats itself. The second star eventually swells, goes through its own giant phase, and then it too collapses and explodes in a supernova. It too must survive the violence of its own birth kick. If against all these odds, after all these cosmic trials and tribulations, the pair remains gravitationally bound, you are left with the final product. Two black holes born from two companion stars now orbiting each other in a tight, stable embrace, their fate sealed. All that remains is the slow, inexorable work of gravitational radiation, the gentle bleeding away of orbital energy over billions of years, drawing them closer and closer, second by second, millennium by millennium, until they finally touch and merge, sending that telltale chirp across the cosmos to us. It is an elegant, compelling story, a tale of fidelity of a cosmic pair that was born together, lived together, and ultimately died together. It explains how you can get two black holes close enough to merge within the age of the universe. But as the catalogue of mergers grew, this story began to show some strain. Some of the black holes we were detecting had spins that were strange. In the isolated binary model, you would expect the two original stars formed from the same rotating cloud of gas to spin in roughly the same direction. Like two ice skaters spinning side by side, their axes of rotation should be largely aligned with the axes of their mutual orbit. This alignment should for the most part be preserved even after they collapse into black holes. Yet some of the signals we received hinted at something else entirely. They hinted at chaos. Black holes whose spins were tilted at wild angles, even pointing in the opposite direction, to their orbital motion tumbling through space like poorly thrown footballs. How could a faithful pair born and raised together end up in such a bizarre, misaligned configuration? This clue, the clue of spin, pointed us toward a second, far more violent path. It suggested that some of these pairs were not lifelong companions at all. They were strangers who met late in life, brought together by violence, in one of the most extreme environments the universe has to offer. To explore this possibility, we must leave the lonely quiet of the galactic field and travel to a place of incredible density and chaos. We must go to a globular cluster. Imagine a city of 1 million suns, all crammed into a space only a few dozen light-years across. It's a sphere of ancient glittering stars, a gravitational hornet's nest, where stellar encounters are not a remote possibility, but a statistical certainty. Here the laws of gravity play out in their most brutal fashion. Over billions of years, the most massive objects in the cluster are subjected to a process called dynamical friction. Just as a marble rolling through honey is slowed down, massive stars and black holes moving through the cluster's star field are constantly tugged upon by the smaller stars they pass. This relentless series of tiny gravitational handshakes saps their momentum, causing them to sink slowly but inexorably towards the cluster's core. The centre of a globular cluster therefore becomes a dark jewel box, a dense concentration of the cluster's heaviest remnants, neutron stars and especially black holes. What you create is a celestial mosh pit, a gravitational billiard table, where dozens of black holes are locked in a chaotic dance. In this maelstrom, anything can happen. A black hole might encounter an existing binary star system. In a complex three-body interaction, the black hole can use its immense gravity to violently eject one of the original stars and take its place, forming a new, tighter binary with the remaining star. Or even more dramatically, two separate black holes can find each other. They might encounter a third black hole which can act as a gravitational catalyst, absorbing orbital energy and flinging itself away, leaving the first two black holes locked in a new tight orbit. This is the dynamical capture model. It's a story not of fidelity, but of brutal matchmaking in a cosmic metropolis. And this model makes a very different prediction about spin. Because these black holes are strangers captured from random directions, there is no reason for their spins to be aligned. One could be spinning forwards, the other backwards. One could be spinning vertically, the other horizontally relative to their orbit. Their spins would be completely randomized, a signature of their chaotic origins. The observation of wildly misaligned spins in some mergers is a powerful piece of evidence for this violent pathway. Suddenly, we had two compelling but mutually exclusive narratives: the faithful couple and the violent encounter. The universe, it seemed, was using more than one recipe to cook up these catastrophic events. The question then became, which method is more common? Are we mostly seeing the end products of isolated pairs living out their lives in the galactic wilderness? Or are we primarily eavesdropping on the final screams from the chaotic cores of stellar cities? The answer is written in the fine details of the gravitational waves themselves. It's a cosmic forensics problem of the highest order. We sift through the data of each new merger, looking for the telltale signs. Is the spin alignment orderly, suggesting a field binary, or is it chaotic, pointing to a globular cluster? We look at the masses. dynamical interactions in clusters can build up more massive black holes through a sequence of repeated mergers, potentially explaining some of the true behemoths that LIGO and Virgo have uncovered, monsters that are difficult to create from a single pair of stars. We even look for a subtle property called eccentricity. A binary formed in isolation will have had billions of years for its orbit to circularize, smoothed out by gravitational radiation. Its final dance will be on a near-perfect circular path. But a pair formed dynamically just before a merger might not have had time to settle down. They might plunge towards each other on a more elliptical or eccentric orbit. Detecting even a hint of this eccentricity in the gravitational wave signal would be a smoking gun for a dynamic origin. But the universe is never so simple as to give us a clean answer. As more data flowed in, the picture became blurrier, not sharper. We found events that looked like perfect examples of isolated evolution, with well-behaved spins. We found others that screamed of chaotic capture, and we found some that were ambiguous, sitting uncomfortably in the middle. It seemed both channels were open for business. The universe was not choosing one path, but using all available avenues to bring its black holes together. And this realization opened yet another door into an even darker room. If both these pathways are active, what else might be happening? Are there other, even more exotic ways to form these binaries? Perhaps in the turbulent gas-rich disks surrounding the supermassive black holes that lurk in the hearts of galaxies like our own Milky Way. In these cosmic whirlpools, smaller black holes might get swept along their orbits, decaying rapidly as they plough through the dense gas-finding partners and merging in a completely different kind of crucible. This third possibility, a galactic nucleus channel, adds another layer of complexity, another suspect in our cosmic lineup. The simple act of opening a new window onto the universe did not just solve old mysteries, it created a host of new ones. Each gravitational wave that washes over our planet is a fossil, a preserved remnant of a history we are only just learning to read. Within the complex shape of that simple chirp, in the subtle variations of its pitch and amplitude, lies the entire life story of the system that created it. Was it a story of coevolution and fidelity, or one of violence, theft and chaos, or something else entirely? We are no longer just astronomers. We are becoming gravitational archaeologists, sifting through the ruins of cosmic collisions, trying to reconstruct the lives that led to these spectacular deaths. The downward path into this new science is not one of discouragement, but of ever-expanding possibility. The universe we are learning is more imaginative, more varied and more violent than we had ever dared to believe. And with every new merger detected, the chorus of the dark universe grows louder, its voices more distinct, each one adding a new verse to a story that is only just beginning to be told. And so the silence was broken. Not just once in a fleeting triumphant chirp that rewrote our story, but again and again, and then with a cadence that became almost familiar, a cosmic drumbeat echoing from the farthest shores of spacetime. Each event, once a miracle, became a data point. Each collision, once a revelation, became a single verse in a growing epic. The era of discovery had gracefully, inexorably given way to the era of understanding. We had opened a new set of eyes, and with them we began to build a library not of words but of echoes from the end of existence. This expanding catalogue of cataclysms is more than just a collection. It is a revolutionary new instrument for cosmic exploration. Each binary black hole merger is a self-contained physics experiment, a laboratory forged in the heart of a dying star system, and delivered to us across billions of light years. An experiment designed to test the absolute limits of our most profound theory of gravity. For a century, Albert Einstein's general relativity has been our guide, predicting with unnerving accuracy everything from the orbit of Mercury to the bending of starlight around the Sun. It has passed every test we've thrown at it, but always in realms of gentle curves where space-time is merely warped, not shredded and resewn. The final moments of a black hole merger are nothing like that. This is not a gentle slope, this is a vertical cliff. Here in the frantic final spiral gravity is millions of times stronger than anything found on the surface of a neutron star. Space-time is not just curved, it is whipped into a violent relativistic storm. This is the ultimate stress test, the one arena Einstein himself could only imagine. And with every new signal we are pushing his theory into that crucible. The waveform we receive, that simple rising chirp, is encoded with the entire story, a gravitational symphony in 3 movements each, a unique test of relativity. The first movement, the long, slow inspiral, is a meticulous validation. As the 2 black holes circle each other, they radiate energy away as gravitational waves are processed that robs them of orbital momentum and pulls them closer. General relativity provides an exquisitely precise mathematical formula for how much energy should be lost at every single moment. This formula dictates the exact rate at which the chirp's frequency should rise. We listen as these 2 monsters, perhaps a billion light years away, follow the relativistic choreography written down by a physicist a century ago. They do not deviate. The frequency climbs exactly as predicted. The orbital decay matches the equations to an astonishing number of decimal places. It's as if the universe is using an incorruptible celestial calculator, and the answer it provides is time and again Einstein. But it is the final 2 movements, the merger and the ringdown, where the most profound truths are laid bare. The merger is the chaotic crescendo, a moment of pure, unadulterated violence, where 2 distinct regions of spacetime, 2 separate singularities are crushed together into one. Our supercomputers running simulations based on Einstein's equations struggle to model this moment of sheer computational insanity. Yet the waves that emerge from this simulated chaos perfectly match the waves we observe with LIGO and Virgo. The theory holds even in the heart of the inferno. Then comes the final, most elegant test of all the ringdown. After the violence of the merger, the newly formed misshapen black hole must settle into its final stable state. It quivers shuddering like a struck bell, shedding its deformities, as a final burst of pure gravitational waves. This is where one of the most bizarre and beautiful concepts in physics is tested, the no-hair theorem. This theorem predicts that a black hole, once it settles, is the simplest object imaginable. It has no mountains, no continents, no complex chemistry, no hair. Its identity can be defined by only 2 numbers, its mass and its spin. That's it. All other information about the 2 stars that died to create it, all the complexity of the matter they consumed, is erased from existence. And just like a bell of a specific size and material will always ring with the same pure tone, a black hole of a specific mass, and spin should ring with a very specific set of frequencies. The ringdown is the sound of space-time itself snapping back into equilibrium. It is the universe's fundamental frequency accord played on the fabric of reality. With our detectors we listen to these celestial bells. We measure the frequency and the decay time of their ringing. From these numbers we can calculate the mass and spin of the final black hole. Then we look back at the inspiral phase and calculate the mass and spin of the 2 original black holes before they merged. We add them up, account for the stupendous energy lost to gravitational waves, and predict what the final object should be. These 2 calculations, one from the beginning of the signal and one from the end, give us 2 independent measurements of the very same object. Do they match? Do the properties of the infant black hole deduced from its first cries align with the properties of its parents? Every single time the answer has been a resounding yes. The universe, it seems, respects the law. The no-hair theorem holds. The black holes we observe are as bare, as simple, and as terrifyingly pure as the theory demands. Through this cosmic laboratory, we are not just confirming a century-old idea, we are proving that its laws govern the most extreme interactions in the cosmos, forged in conditions we can never hope to replicate on Earth. But testing the fundamental laws of gravity is only the beginning of the story. With each merger, we are doing more than just verifying equations. We are taking a census of the universe's most elusive inhabitants. We are becoming cosmic archaeologists, unearthing the fossil record of the most massive stars that have ever lived and died. Before gravitational waves, our knowledge of black holes was frustratingly incomplete. We could find them only if they were actively feeding on a nearby star, unleashing brilliant flares of X-rays that gave away their position. This was like trying to understand the population of predators in a jungle by only looking for them at the exact moment they were making a kill. We knew we were missing the vast, silent majority, the millions of solitary hunters prowling the darkness of the Milky Way and beyond. Gravitational waves changed everything. Now we hear them not when they eat, but when they meet their own kind. This has allowed us to build the first ever galactic census of these dark remnants, and the initial results have been utterly astonishing, forcing us to rewrite entire chapters of stellar evolution. Our models, based on observing stars in our own cosmic neighbourhood, had predicted a kind of stellar weight limit. We believed that stars born with more than about 130 times the mass of our Sun would meet a uniquely spectacular and self-destructive end. In their final moments, their cores would become so hot that they would generate gamma rays energetic enough to spontaneously produce pairs of electrons and positrons. This process, called pair instability, would rob the core of its pressure support, triggering a runaway thermonuclear explosion of unimaginable power. Unlike a normal supernova that leaves a black hole behind a pair instability supernova, would be so violent it would blow the star to smithereens, leaving not a single remnant behind. Not a black hole, not a neutron star, nothing. This created a predicted upper mass gap, a forbidden desert in the cosmic graveyard between about 65 and 120 solar masses, where no black holes should exist. It was a neat, tidy theory born from our best understanding of nuclear physics. And then on May 21, 2019, our detectors picked up a signal, GW190521. It was a faint, short, low-frequency tremor from 5 billion light-years away, lasting less than 1/10 of a second. But its implications were staggering. The signal came from the merger of two black holes, one weighing 66 solar masses, and the other a colossal 85. The 85 solar mass black hole was sitting squarely in the middle of the forbidden zone. It was a ghost in the graveyard, an object our theories insisted could not exist. How was it formed? Perhaps it was itself the product of a previous merger, a second-generation black hole. Or perhaps our theories about the final moments of the most massive stars are wrong, or at least incomplete. Maybe some stars are so enormous they can collapse directly somehow, skipping past the self-destructive pair instability process. This single event, a brief tremor from a distant galaxy, threw down a gauntlet to astrophysicists everywhere. It proved that the universe is more imaginative in building its monsters than we had ever given it credit for. At the other end of the scale, we are solving another long-standing puzzle, the lower mass gap between the heaviest possible neutron stars and the lightest possible black holes. Theory suggested that neutron stars should collapse under their own weight if they grow beyond about 2.5 times the mass of the Sun. Yet the lightest black holes we had ever found through X-ray observations were all heavier than about 5 solar masses. So what happens in between? Does nature simply not build objects in this range? Gravitational waves are now providing the answer. We have started to find mergers involving objects right in this mysterious gap, blurring the line between the most extreme stars and the least extreme black holes. We have seen a 2.6 solar mass object, a true enigma, merging with a 23 solar mass black hole. Was it the heaviest neutron star ever found, or the lightest black hole? We may never know for certain, but its very existence shows us that this supposed gap is not an empty desert, but a frontier waiting to be explored. Beyond just their mass, the catalogue is revealing another crucial clue to the life stories of these binaries, their spin. Just like a spinning skater pulls in their arms to speed up a collapsing star, spins faster and faster, conserving its angular momentum. This means that nearly all black holes should be born spinning some at near light speed. When two black holes form together from a pair of orbiting stars, a common scenario for massive stars, they should evolve in gravitational lockstep. Their axes of rotation, their personal north and south poles should be neatly aligned with each other and with the axis of their orbit like a perfectly synchronized pair of ice dancers. If we detect a merger where the spins are aligned, we can be fairly certain we are witnessing the end of a lifelong isolated partnership. But there is another way to form a binary black hole through violent capture. In the chaotic, crowded downtown of a globular cluster, a dense ancient swarm of millions of stars' black holes can sink to the core and engage in a complex gravitational dance. They can sling each other around eject-lighter stars, and eventually two of them will capture each other as a binary pair. In this scenario, their spins would be completely random. One might be spinning upright, the other on its side, another even upside down, like two strangers thrown together on a dance floor. By measuring the spins from the subtle modulations they impart on the gravitational waveform, we can distinguish between these two formation channels. We can ask, where are the universe's most prolific black hole nurseries? Are they in the quiet solitude of the galactic field, or in the brutal mosh pits at the hearts of globular clusters, the data so far suggests both. We see evidence for neatly aligned systems, and we see evidence for wildly tumbling chaotic pairs. It tells us that nature is not monolithic in its methods. It employs every tool at its disposal to bring its darkest creations together. Each new detection adds a vital statistic to this cosmic survey, allowing us to map the distribution of black holes through space and time, refining our models of how stars live, how they die, and how their corpses congregate in the darkness. From the bedrock of fundamental physics to the grand tapestry of stellar evolution, these mergers are providing answers. But their power as probes of the universe extends even further into the vast realm of cosmology itself. For a century, our primary tool for measuring the cosmos has been light. We discovered the expansion of the universe by observing the redshift of distant galaxies. We chart its structure using the light of so-called standard candles, like type Ia supernovae whose intrinsic brightness we think we know. By comparing how bright they appear to how bright they should be, we can calculate their distance, and from that the expansion rate of the universe. But now we have an entirely new and independent way to measure cosmic distance. A binary black hole merger is not a standard candle, it is a standard siren. The physics of general relativity allows us to calculate directly from the gravitational wave signal the intrinsic amplitude of the waves, the true volume of the siren. By measuring the amplitude we actually detect here on Earth, we can determine precisely how far away the merger occurred. It is a cosmic tape measure of unparalleled purity, one that doesn't rely on a complex and messy ladder of astronomical distance estimations. There's just one catch: a black hole merger by itself is dark. The siren wails, but we don't know exactly which galaxy it came from. But in 2017 we saw the exception that proved the rule. We witnessed the collision of two neutron stars, an event that produced not only gravitational waves, but also a spectacular flash of light, a kilonova, that allowed us to pinpoint its host galaxy. We had the distance from the standard siren and we had the redshift from the light. Putting them together gave us a completely independent measurement of the Hubble constant, the current expansion rate of the universe. This is critically important because right now cosmology is facing a crisis. Measurements of the Hubble constant using standard candles in the nearby universe disagree with measurements derived from the cosmic microwave background, the echo of the Big Bang. It's a tension that could be pointing towards new physics. Standard sirens offer a third decisive way to break the tie. With dozens of these events, we can refine our measurement of the Hubble constant, and perhaps solve one of the biggest puzzles in modern cosmology. Even without a light show, we can still do cosmology. For each dark siren, we can look at all the potential host galaxies in that patch of sky, and use statistical methods to home in on the most likely expansion rate. It's less precise for a single event, but with the hundreds of mergers we now have, the statistics are becoming powerful. We are building a new map of our expanding universe drawn not with photons, but with gravity. This is a whole new sense for humanity, a new window onto the cosmos that is only just beginning to open. The expanding catalogue of mergers has become a toolkit of unprecedented power, a gravitational scalpel for dissecting the universe's greatest secrets. We are testing the very fabric of spacetime under duress, and Einstein's ghost so far is smiling. We are conducting a census of the stellar dead, uncovering new and unexpected populations that are forcing us to rethink the lives of stars. And we are measuring the universe itself, its age, its expansion, its ultimate fate, with a ruler forged from the collision of monsters. Yet for all the answers we have found, each new signal seems to whisper of deeper questions. With every new detection, we sift through the data, not just for confirmations, but for anomalies, for the slight deviation that doesn't fit the model. We search for faint echoes in the aftermath of the ringdown, a signature that might betray the existence of something other than a pure vacuum at the event horizon. We look for the telltale signs of exotic physics of extra dimensions, or of a breakdown in relativity that could herald the next great scientific revolution. We have not found it yet. But we have found something else. In the growing list of colliding objects, we have started to see hints of a new class of black hole, something that bridges the vast gap between the stellar mass corpses we have been studying and the supermassive behemoths that dwell at the centres of galaxies. A missing link in cosmic evolution whose origins are a complete mystery. The hunt for these intermediate mass black holes is on, and the answers may lie within the next gravitational wave we detect a signal that could finally reveal how the universe builds its true titans. And so, the silence of the cosmos is broken forever. For a century we peered into the void blind to its most violent upheavals. We saw the placid embers of dead stars, the serene glow of distant galaxies, believing that what we saw was all there was. We were a species deaf to the true music of the spheres, a thunderous symphony of space-time shaking at the seams. The journey from a curious scribble in Einstein's notebook, a mathematical ghost he himself found difficult to believe in, to the first faint rising chirp in a Louisiana laboratory, has been one of humanity's greatest intellectual odysseys. It was a voyage not across space, but into a new mode of perception, a quest to build an entirely new sense for ourselves. We sought to hear the unheard, to touch the intangible fabric of reality, and in doing so we have irrevocably transformed our place in the universe. We are no longer just spectators watching ancient light. We are now participants feeling the very pulse of creation, the reverberations of events so extreme, so alien, they defy the comfortable confines of our terrestrial intuition. Every detection we've shared in this story is more than a data point. It is the final, desperate cry of a world that has ceased to exist, an echo that has travelled for 1 billion years to whisper its secrets to us. It is the universe speaking to itself, and we finally are learning the language. From those first few tentative detections, a revolution has bloomed. The trickle of discovery has become a torrent, a relentless flood of cosmic collisions that has reshaped entire fields of astrophysics. We have witnessed the birth of black holes in real time, confirming that these impossible objects are not mere theoretical curiosities, but common active and vital players on the cosmic stage. We watched as two voids each, a prison for light and matter, danced a gravitational minuet of accelerating fury, their death spiral proving Einstein's predictions with breathtaking fidelity. In the crucible of their merger, in that final violent ringdown, we have seen spacetime itself behaving like a struck bell, its quivering vibrations a perfect match for the mathematics of relativity. This was no gentle confirmation. This was the ultimate stress test, a glimpse into the physics of the strong field regime where gravity is not a gentle curve but a cliff edge, and general relativity has passed every single time with flying colours. Beyond this profound validation, we have begun to draw a new map of the cosmos, a family tree of its darkest and most massive inhabitants. Before this new era, black holes of stellar mass were elusive phantoms, their existence inferred only by their subtle influence on a companion star. Now we have a census, a growing catalogue of these collapsed titans. We discovered a population of black holes far heavier than we expected, forcing us to rethink the final explosive stages of the most massive stars. We filled in the mysterious mass gap, a strange desert in our theories between the heaviest neutron stars and the lightest black holes. We found that nature in its infinite creativity knows how to bridge that gap, and we've seen them in all their diversity near equal partners in a balanced dance and mismatched pairs, the larger monster swallowing its companion whole, producing a gravitational scream rich with complex harmonics. Their spins, the fossilized angular momentum from their parent stars have told us stories of their upbringing. Some pairs spin in graceful alignment, suggesting a quiet life, two stars born together, living together, and dying together in a binary embrace. Others are wildly misaligned, tumbling through space like chaotic gyroscopes, a clear sign of a violent, turbulent past in the chaotic mosh pit of a dense star cluster, where they were captured and bound by chance. Through these ghostly whispers, we are becoming cosmic archaeologists, reconstructing the lives and social dynamics of stars long since vanished. This is not just astronomy. It is a form of cosmic genealogy. We are tracing the lineage of the universe's ultimate predators, understanding their habitats, their behaviours, their place in the cosmic food web. And the revelations extend far beyond the nature of black holes themselves. By combining the gravitational shudders with the flash of light, from the collision of neutron stars we unlocked one of nature's deepest secrets. We solved the puzzle of where the universe forges its heaviest elements. You are alive today. The world around you is solid because of these events. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers our reactors, these are not born in the hearts of typical stars. They are the exotic shrapnel of neutron star mergers, cosmic alchemy performed in a cataclysm lasting mere seconds, then flung across the galaxy to seed the next generation of stars and planets. When you hold a piece of gold, you are holding a fragment of a cosmic collision, a tangible remnant of a gravitational wave event. Even the grandest cosmological questions are now within our grasp. These mergers, these standard sirens, are providing an entirely new cosmic yardstick. By measuring the strain of the waves, we can calculate the distance to the collision, and by identifying the host galaxy, we can measure its redshift, its speed of recession. Distance and speed, the two essential ingredients needed to measure the expansion rate of the universe, the Hubble constant. This new method, completely independent of all others, is helping us arbitrate a growing troubling tension in cosmology, a discrepancy in our measurements that hints at potentially new physics. The echoes of colliding black holes are helping us take the measure of the entire observable universe from its origins to its ultimate fate. We have come so far listening to these faint tremors in spacetime. But everything we have detected, every single chirp, is just the beginning. It is the sound from the shore of a vast uncharted ocean of cosmic phenomena. The instruments we have built are magnificent, but they are the first generation. They are the stone tools of a new science, and the age of steel is coming. On the ground, we are planning for successors to LIGO and Virgo observatories of such immense scale and sensitivity they almost beg a belief. Imagine the Cosmic Explorer, a colossal L-shaped detector, its arms stretching not 4 but 40 kilometers through the Earth. Imagine the Einstein telescope, a technological cathedral buried deep underground, an equilateral triangle of tunnels 10 kilometers on a side shielding it from the seismic noise of our own restless planet. These future terrestrial ears will be so exquisitely sensitive that they will detect every single stellar mass black hole merger happening anywhere in the observable universe. There will be no hiding place. The quiet hum of our current detectors will become a roar, a continuous stream of chirps, one blending into the next. The sky will be alive with gravitational waves, a constant crackling symphony. We won't be hunting for individual events. We will be grappling with an avalanche of data transforming gravitational wave astronomy into a precision science. We will map the expansion history of the universe in fine detail, watching how dark energy has shaped our cosmos through the eons. With this new depth, we will be able to hear the faintest whispers, the mergers of black holes from the dawn of time, the very first generation of stars to light up the cosmic dark ages. These were the true giants, pristine monsters made of pure hydrogen and helium, and their deaths would have created black holes of unimaginable size. Listening for their distant red-shifted death cries is like cosmic archaeology, allowing us to probe an era forever opaque to our light-based telescopes. We will hear the formation of the first cosmic structures, the gravitational seeds, from which the great galaxies would later grow. The Einstein telescope and Cosmic Explorer will not just be observatories, they will be time machines tuned to the frequency of creation. And they will listen for something more profound, a constant steady hum. The stochastic gravitational wave background. This isn't the sound of one collision, but the combined overlapping murmur of every unresolved binary black hole and neutron star merger that has ever occurred throughout cosmic history. It is the ultimate background noise of the universe, a subtle hiss that encodes the entire history of star formation and death. Decoding this hum will be like standing in the middle of a crowded stadium and from the indistinct roar of the crowd discerning the entire history of the game. But even these incredible terrestrial projects are fundamentally limited. The constant trembling of our planet, the pull of our own gravity, blinds them to the lowest frequencies of the gravitational wave spectrum. To hear the deepest, slowest, most powerful notes in the cosmic symphony, we must leave our world behind entirely. We must build an observatory not on Earth, but of space itself. This is the vision of LISA, the Laser Interferometer Space Antenna. It is an instrument of breathtaking ambition, a detector on a scale we have never attempted. Imagine 3 spacecraft flying in a perfect triangular formation, orbiting the Sun in the silent, stable vacuum far behind the Earth. These spacecraft are not kilometers apart, but 2.5 million kilometers apart. They form a gravitational wave antenna larger than any planet, a celestial triangle, held together by the invisible threads of laser light. The entire formation will breathe in and out as gravitational waves pass by, and by measuring these minuscule changes in distance, changes smaller than the width of a single atom over millions of kilometers, LISA will open a completely new window onto the cosmos. It will be deaf to the high-pitched chirps of stellar mass black holes. Instead, it is tuned to the majestic low-frequency rumble of the true titans, the supermassive black holes that dwell in the hearts of every major galaxy. These are the monsters 1,000,000 or 1,000,000,000 times the mass of our Sun. When galaxies collide, as they frequently do, these giants begin a slow, inexorable dance of death that can last for hundreds of millions of years. LISA will hear the final stages of this cosmic waltz. It will detect the signal from these merging behemoths, not for seconds, but for weeks, months, or even years before their final universe-shaking collision. We will hear the crescendo building, tracking them as they spiral closer and closer. This will be the ultimate multi-messenger event. LISA will act as a cosmic early warning system, telling telescopes on Earth and in orbit exactly where in the sky to look and when to witness the explosive fireworks of gas and light that are expected to accompany the merger of two galactic hearts. For the first time, we will see and hear simultaneously the most energetic events in the universe since the Big Bang itself. LISA will also probe the most extreme gravitational systems, imaginable objects known as extreme mass ratio inspirals, or EMREs. These occur when a small stellar mass black hole is captured into a complex spiraling orbit around a supermassive one. For thousands upon thousands of orbits over many years, the smaller object acts as a gravitational probe, a tiny explorer. Its signal will be a long, intricate song, a complex waveform that maps the warped, twisted, churning space-time around the central giant with a precision that is simply impossible by any other means. We will be able to test the very fabric of Einstein's theory around a black hole to check if these objects truly have no hair, no features beyond mass and spin. Any deviation from the predicted song would be a revolution, a sign that our understanding of gravity is incomplete. It would be the first whisper of a deeper, more fundamental theory. Between the ground-based observatories and LISA, we will have the entire gravitational wave spectrum covered. From the high-frequency screams of colliding neutron stars to the patient baritone hum of supermassive black holes, we will finally be listening to the full cosmic orchestra. We will chart the growth of black holes from their stellar seeds to the galactic monsters that dominate their ecosystems. We will watch the universe build itself merger by merger from the cosmic dark ages to the present day. This is the promised land for gravitational wave astronomy, a future where we don't just hunt for waves but use them as a tool to explore every facet of the universe from cosmology to fundamental physics. It is a future where our sky is not just a canopy of lights, but a vibrant dynamic soundscape of constant activity. And perhaps the most thrilling promise is the one we cannot yet articulate. The promise of the unknown. Every time we have opened a new window on the universe from Galileo's first telescope to the radio dishes of the 20th century, we have been surprised. We have found things we never thought to look for. What other exotic objects might be ringing the bell of space-time? Could the waves reveal the existence of cosmic strings, hypothetical defects in the fabric of reality left over from the Big Bang? Could the collisions of bizarre objects like boson stars be lurking in the data, their gravitational wave signature, unlike anything we've seen before? Could the very nature of the waves themselves, their polarization, their speed, reveal secrets about the nature of gravity, hinting at extra dimensions or the first clues of a quantum theory of gravity? The black hole mergers we have detected are the loud, obvious sounds in a cosmos that is surely filled with more subtle and stranger music. We are standing at a profound turning point in our history. For millennia, we have strained our eyes to see the light. Now we have taught ourselves to listen to the silence. We have built ears from lasers and mirrors, and with them we have heard the echoes of infinity. The journey is far from over. The greatest discoveries, the deepest mysteries, the most universe-altering revelations are still out there vibrating through the cosmos, waiting for us to listen. The symphony has just begun, and its final, most breathtaking movements are yet to be written and yet to be heard. The story of the universe is not just written in light, it is sung in the key of gravity. and our ability to hear that song is just now awakening.